Hey, so let's talk about some acids and bases. These are some examples. It would have been nice if we could do the lab where you kind of test the pH of some things, but soda, tomatoes, weak acid, milk, I guess if it's sour. I don't know that that's really bad. Vinegar, lemon juice, stomach acid are much stronger. Water is neutral. Toothpaste, baking soda are weak bases. And when you get stung by a wasp, or if you use oven cleaner or any cleaners, those tend to be bases. All right. So, a good thing for you to know, if you learn nothing else, the Arrhenius theory of acids works really well. He basically said an acid would produce H plus in water. Sometimes I might call that a proton, and a base will produce OH minus in water. And basically, here's the classic example: HCl will dissociate into H plus and Cl minus, and sodium hydroxide will dissociate into Na plus and OH minus. So that H plus and OH minus are the keys here to an acid and a base. This is just that Arrhenius also came up with back then when he was alive that carbon dioxide was probably not good for the environment. So he figured that out first. So when I call H plus a proton, if you think about what hydrogen is, it's a proton and an electron. And basically, if we were to get rid of that, we would have a plus charge. And that means all that's left is a proton. So H plus is basically just a proton. And the beauty of all acids and bases is when they come together, they form water. H plus with OH minus will form water. In fact, there are some teachers who will take concentrated acid and then show you how concentrated it is by dissolving metal in it or something, and then a strong base and dissolve something in the base and then mix them perfectly together so that they make water and then drink it. So I will not do that because that's not good if you don't do it perfectly correctly. So the other things, what about the sodium and the, right, here's the sodium and the chlorine. What are they doing? Well, we call those spectator ions because they don't do much. They just sort of watch what's happening. They're not anything of import in these reactions. We're more interested in the H plus and the OH minus. Okay, so here are some acids. We talked about this back when we were naming things. Acids always start with an H, a leading H anion. Typical formula, H, A being the rest of the acid. How many H's you need, because each one's a plus one, is dependent upon the anion, the negative part, and how many charges they need. So chlorine, you remember, as a chloride ion is minus one. So it would need one H plus. HBr, Br is minus one, so it would need one. SO4 is minus two, so that would need two plus ones to equal zero. PO4 is minus three, so that would need three H's to equal zero. Remember this back when we were doing this. So weak acids, you should know: acetic acid, citric acid, vitamin C, ascorbic acid, formic acid. These are all weak acids. Formic acid comes from ants. Vinegar is a weak acid, right? You can drink that. It doesn't drive you nuts. Citric acid doesn't drive you nuts. So we were talking about how that's what's in flavor enhancers. So those are things that are weak enough that you can run through them in your body and it won't do you any harm. So think of an acid as basically H plus acting like an ionic metal, right? Instead of being stuck in a covalent bond, acids have H pluses that dissociate like a sodium or a potassium might. So bases are typically, if they're strong bases, it's going to be a metal plus OH minus. Again, the charge of the metal will determine how much OH minuses you need. So sodium has a charge of plus one, so it needs one OH minus. Calcium has a charge of plus two, so it needs two OH minuses to equal zero. Weak base wise, we're going to basically go with amines, things with a nitrogen on it. That nitrogen has a basic lone pair. We'll talk about that later. But so ammonia, triethylamine, anything with a nitrogen in it will be considered a weak base. Anything with an OH will be considered a stronger base. H pluses are true of all acids. The weak acids are like citric acid, acetic acid, ascorbic acid. All right, so basically, can you identify these things as an acid or a base? Here, we don't have a leading H and we have an OH, so that would be a base. Here we have a leading H, so that's an acid. Here we have a nitrogen, no leading H, so that's a base. It's actually a weak base. Here's a nitrogen again, not the leading H. It has an H, but it's not leading. So that's a base. Calcium hydroxide, OH, right? No leading H, that's a base. Lithium hydroxide, that's a base. H3PO4, H is leading, so that's an acid. HCN, right? H is leading, so that's an acid. N, right? You got your OH, you got your nitrogen with no leading H, that's a base. HC2H3, that's acetic acid, so that's an acid. All right, so you should be able to determine acid or base. You're looking for leading H's for acids. Bases will start with a nitrogen or have an OH in them. All right, so remember the concept of equilibrium. I talked about my cat and how he's asleep some of the time and he's awake some of the time. And if we really broke it down, he'd be asleep like 60% of the time and he'd be awake 40% of the time. And that's what equilibrium is. It doesn't mean they're equal. It just means that at some point you have a split that doesn't change. So pretty much on a daily basis, the cat's asleep 60% of the time and awake 40% of the time. So that's true with chemicals as well. You can have products and reactants in a split. And that's basically what will determine a strong acid versus a weak acid. A strong acid has a whole lot of H plus dissociated. Let's say 95% of your H plus is dissociated and 5% stays with the acid. On a weak acid, that would be more 50-50. So 50% of the time, the H plus is with the acetate, and 50% of the time, it's all alone. Okay, so here H is all alone, here it's stuck, here H is stuck, here H is all alone. That H plus can do damage, and so weak acids tend to hold their H's back on the anion. And another way to think about that, a weak acid is like a dog on a leash, whereas a strong acid is the dog all on its own, right? So if the dog is the H plus, right? So you're not quite as worried about a dog that has a person with a leash holding it from doing any damage. When that dog is off the leash, that's when you got to worry about it. And that's what a strong acid is. All right, so here's a picture of a weak acid in the FET you're going to do or did. I've sort of filled in these gray molecules are supposed to be this HA, right? So here's your hydrogen, and it also has your anion connected to it. There you go, right? So I've done some of those here. So if they're connected, that's a weak acid. So any of these gray structures, the H is connected and therefore not causing all the damage. The red ones here are the acid doing the damage when it reconnects with water. That's a weak acid. Notice the difference between that and a strong acid, right? Strong acid doesn't have any of these gray things in there because all the H plus dissociates and goes out and does the damage. So these H pluses are, they're connected to water. What the theory is if you have a proton, it wouldn't just exist all by itself because it's too charged. So what it's going to do is going to jump onto a water, right? A water molecule which has a negative charge on the oxygen. It's just going to stick to that. That's why it's H3O plus. So anyway, there you go. Strong acid versus weak acid. You're on the leash, right? You're stuck to that anion pretty much most of the time. Whereas strong acid, you're often on your own. All right, so Bronsted Lowry had another definition, and this leads into what we were just looking at. An acid is a proton donor, so H plus goes to H3O plus, right? H3O would have an extra hydrogen, so one will fall off. That's what an acid is. And a base is a proton acceptor. So a base doesn't have to just be, as Arrhenius said, an OH minus, right? The beautiful thing about OH minus is that it's capable of grabbing an H plus and becoming water. That's very simple. But what about nitrogens, right? Nitrogen has this lone pair. There's no reason an H plus can't just park on there and hang out. And that would make this a base. So anything that can suck up an H plus would be considered a base. Anything that can release an H plus would be considered an acid. So, and then we'll talk a little bit, right, about, we've seen this already, that constants can be limiting. If there's only a certain number of M&Ms that I can fit into an Easter egg, then then as one goes up, the other one goes down. So as I increase the number of yellow M&Ms, I have to take out white M&Ms. And we talked about how this is an inverse relationship, right? So therefore, if I told you that this, the H plus concentration times the OH minus concentration, if I told you that those two things equal a constant that's 10 to the minus 14, okay, then as one of these goes up, the other one has to go down, right? Because they're stuck by this constant. So remember math with tens, right? 10 to the fifth has 5 zeros. 10 to the minus 14 has 13 zeros until the 1. It's 1 over 10 14ths. If you multiply them, you add your exponents. If you have negative exponents, you still combine those exponents. So 10 to the minus 6 times 10 to the minus 7 is 10 to the minus 13, right? You're still combining everything. All right, so you should do that. So if all these things have to equal 10 to the minus 14, right, then that means these exponents will add up to 10 to the minus 14. So 10 to the minus 1 times 10 to the minus 13 equals 10 to the minus 14. So as this number gets essentially smaller because it's becoming more negative and the decimals are becoming larger, this number is going up so that they would all equal 10 to the minus 14. Now, I know you don't love that, so let's take a look. Let's take a look at that in action. All right, so if I increase, here's my water with H pluses are red and the OH minuses are blue. If I add more OHs would be this side, then I have to take those H pluses out, right? Because the two of them are going to equal 10 to the minus 14. And likewise, if I'm going to increase my H pluses, I have to take OH minuses out. So if these two things are always going to equal 10 to the minus 14, if one goes up, the other one goes down. So you see how that works? All right. So that's what's being graphed here. As one goes up, the other goes down. So as the H plus is going down, the OH minus is going up. Now down here, you can see it's kind of blah because they're so close to the axis that there's nothing really to happen there. So that's why we have to embrace the log function on our calculators. The log function, what it does is it says 10 to what power will equal, like this number here is the power that 10 is to when you take the log of it. So if I say the log of 10 to the smiley face, that would equal what number there is up there, the smiley face. So 10 to the 43rd, the log of that is the power of 10, 43rd. 10 to the minus 5th, the log of that is the power of 10, the minus 5. So we define pH, which you've heard if you've ever been to a pool or had a fish tank, right? pH is the negative, so the negative log of H plus, because if you go back here, right, all those H plus charges, all these exponents are negative. So people don't like negative numbers, so we just make this negative of the log of that. So if we have 10 to the minus 6, the log of that is minus 6, and then we want the negative log of that, which makes it therefore positive. So negative 6 is positive 6. 10 to the minus 10, pH would be the log of 10 to the minus 10, which is basically minus 10. And then we want to make it positive, so it's negative 10, which is positive 10. All right, so let's do some practice. If we had 0.1, that would be 10 to the negative 1, right? The log of that would be negative 1. The negative log of that would be negative 1, which is positive 1. And therefore the pH is 1, right? The log of 10 to the minus 3 is minus 3. The negative log of that log, minus 3, equals plus 3. So the pH would be 3. Right, so the log of 10 to the minus 5 is minus 5. The negative of that, makes that plus 5. Right, so the log of negative 7, the log of 10 to the minus 7 is minus 7, and then we want to make that positive, so negative 7 is positive 7. Thanks, computer. Right, so negative 10, and we want to make that positive, it becomes positive 10. So the log of 10 to the minus 10 is minus 10, and the negative log makes that positive 10. And this would be plus 14. All right. Why do we take pHs then? Because it makes this U-shaped curve into more of an X shape, right? All these things here, minus 13 becomes plus 13, and minus 1 becomes plus 1. So now these two things equal 14, not 10 to the minus 14. That's nice and easy to remember. And instead, what we have is an X instead of this weird U. So the point of all that is the pH of 1 to 6 means the concentration of H is greater than OH, right? So pH of 1 to 6 means that your concentration of H, right, this number is is larger than these base numbers. These 10 to the minus 1 is larger than 10 to the minus 13. 10 to the minus 2 is larger than 10 to the minus 12. So 1 to 6 means protons are more than your OH. 8 to 14 means you have more OH than H plus. And if it's 7, then they're both equal to each other. So pH is 7 right here. I'll do that in green. Right? So that's where they're equal. And then down here is where you have the opposite. Your base is bigger than your acid in its charge. All right, so down here, those numbers are bigger than these numbers. All right, so there it is. Acid bases 101. Hopefully that makes some sense.